Hi everyone, welcome back. So today we're going to continue working on pushing electrons as well as determining frontier molecular orbitals of the reaction between a nucleophile and an electrophile. Okay, so in this video we're going to be working on problem D here, which involves the nucleophile elimination of this, what we're going to call in a few chapters, called a tetrahedral intermediate. So the way in which this works is you take a lone pair from one of the species in our intermediate here, and use this to snap down and form a pi bond while kicking out in a nucleophile. And so really you have two options here. You can use the electrons from oxygen to form a pi bond with carbon and kick out chlorine, or vice versa. You can use the chlorine to snap down, make a pi bond with carbon, and kick out oxygen. Whenever this winds up happening, the nucleophile you want to eliminate is the most stable species. And so in this case, because Cl- is going to be more stable than O2-, we want to kick out the chlorine and not the oxygen. So the way in which this works, oxygen uses its lone pair of electrons to form a pi bond with the carbon right here. Because carbon only wants to make 4 bonds, and because any more bonds it would force it to violate the octet rule, we have to simultaneously break an oxygen-chlorine bond at the same time. And what this winds up producing is our methyl ketone here, plus a chloride leaving group. Remember that a good check of whether you've performed your arrow pushing and you have your products correct is that the net charge of your reactants should equal the net charge of your products. So over here, our alkoxide is negatively charged, so we have a net charge of -1. Where over here, our chloride is negatively charged, so we also have a charge of -1. Okay, so like our previous video, we're now going to determine the frontier molecular orbitals that allow this reaction to happen. And so, same as above, our highest occupied molecular orbital is going to come from the nucleophile, and it's the orbital that houses the electrons that are donated to the electrophile. So in this case, oxygen is using its lone pair of electrons to snap down and form a pi bond. This is our nucleophile. And so our highest occupied molecular orbital winds up being the lone pair of electrons on oxygen, which in this case is in an sp3 hybrid orbital. So our highest occupied molecular orbital will be lone pair of electrons on oxygen, and this is in an sp3 orbital. Okay, so as before, the LUMO winds up being a little bit more challenging to determine. But to do this, we also want to look about what type of bonds are we breaking. So in this case, we are breaking a chlorine-carbon bond. And remember, the way in which we as chemists break bonds is that we add electrons into an anti-bonding orbital. So in this case, we know our electrophile here is the carbon that is bound to chlorine. And so our lowest unoccupied molecular orbital, the orbital which oxygen is going to donate its electrons into, is going to be our carbon-chlorine sigma bond. So for example, we can make a drawing of this so we can get an idea of what's going on. So I'll draw our oxygen a little out of the way up here. Our carbon-chlorine is going to be bound in sigma fashion, which means it's going to have a sigma bonding orbital and a sigma anti-bonding orbital, which we denote with this little star. What oxygen is then able to do is it's able to take its electrons and donate that into our sigma anti-bonding orbital. And this accomplishes two things. This allows oxygen to make a bond with our carbon because the carbon has a lobe of that sigma star orbital right adjacent to it. Additionally, by occupying a sigma star orbital, we're able to break a carbon-chlorine bond, because remember, when we occupy antibonding orbitals, we cancel out the corresponding bonding orbital, i.e., the thing that's holding our carbon and chlorine together. So, to summarize, our LUMO in this case is going to be our carbon-chlorine sigma star orbital. Hope this was helpful, and I'll continue to make some videos on this in the near future. See you soon.